So look at the question number 51. An insect crawls up a hemispherical surface very slowly as shown in the figure. The coefficient of friction between the insect and surface is 1/3. The line joining the center of the hemispherical surface to the insect makes an angle alpha with the vertical. The maximum possible value of alpha is given by. So, if we are given the diagram, let us consider the forces acting on the insect. That means we will consider a situation when the insect has reached the maximum possible height above the lowest position. So that means that the insect is at the verge of sliding down. So the weight mg of the insect acts vertically downwards. The narrow reaction force on the insect by the smooth surface acts perpendicular to the surface in contact and directed away from surface. So Kaplan represents the magnitude of narrow reaction force on the insect by the hemispherical surface, which acts towards the center of curvature of the surface. So at the highest possible position up to which the insect can move up along the spherical surface, it will be about to slip down. That means we consider the position where the insect crawls up the surface to the maximum possible height above the lowest position. So at the highest possible position up to which the insect can move up, it will be about to slip down, about to slide down. Therefore, it will be limiting equilibrium. So the limiting friction acts up along the surface. That means the free body diagram, we can show the limiting friction to be acting almost along the tangent to the surface. So here the line of action of normal reaction is produced backwards. The angle, this angle is alpha, so this will be also alpha. The weight mg, the line of action of the weight mg parallel to this vertical line passing through the center of curvature of the hemispherical surface. So this angle is alpha, so this will be also equal to alpha. So we can resolve this mg into components tangential to the surface and along the normal to the surface. The method is similar to the method we follow for a body resting on the inclined surface. So the surface is not a smooth surface. There is friction between the surface. So the weight mg can resolve it into components here. So mg cos alpha acts perpendicular to surface. Mg sin alpha acts tangential to surface. Because it is a limiting equilibrium, the component mg cos alpha is balanced by normal reaction force. And the limiting friction balances the component mg sin alpha. So therefore you can write us into n equal to mg sin alpha in magnitude and n equal to mg cos alpha in magnitude. So divide the first equation second. So us into n by n is equal to mg sin alpha by mg cos alpha. So when the insect is in limiting equilibrium at the highest possible position, we can write tan alpha equal to nu s. Similar equation we got earlier for a body rest in limiting equilibrium on the rough inclined plane. Here nu s is given to 1 by 3. So tan alpha is 1 by 3. So cot alpha is reciprocal of tan alpha. So you get cot alpha to be equal to 3 or 3 by 1. That's the answer. Come on, copy down the solution of this question. In case you need more time to copy the solution, you can take a pause and take your own time. So for question number 51, first option is the answer. See the question number 52. A cart of mass capital M has a block of mass small m kept in contact with as shown. The coefficient of friction between the block and cart is nu. The minimum acceleration of the cart so that the block small m does not fall is. So if the cart is stationary, we'll consider a situation. The cart is stationary. When the block is stationary with respect to the cart. That means with respect to laboratory frame of reference, the block appears to move along with the cart with the same acceleration as that of the cart. So let us consider the force acting on the block. Its weight mg acts vertically downwards. Let n denote the magnitude of the normal reaction force exerted on the block by surface of the cart, which acts perpendicular to surface of the cart in contact and directed away from surface in contact. So the block will have a tendency to slide down relative to the cart. Therefore, force of friction on the block by the surface of the cart acts tangential to surfaces and upwards. So I choose the horizontal direction, which is the direction of the motion of the cart as positive direction of x-axis and vertically upward direction as y-axis. So we'll solve the problem with respect to the stationary observer on the ground. So when the block does not fall downwards with respect to the cart, that means if the block is stationary with respect to the cart, we can say that the block appears to move horizontally with same acceleration as that of cart, as seen by the stationary observer on the ground. So when the block is stationary with respect to the cart, then for the stationary observer on the ground, the block appears to, with respect to the stationary observer on the ground, the block appears to move horizontally towards right with the same acceleration with the cart moves. So with respect to laboratory frame of reference, we are making the calculation with respect to stationary observer on the ground or with respect to laboratory frame of reference. So y component resultant force you can write Fs minus mg. So the type of friction which exists between the block and surface of the cart can be called as static friction when the block is stationary at rest with respect to the cart. So this must be 0 because the block has no motion in the vertical direction. So magnitude of static friction on the block by surface of cart should be equal to mg. So resultant force on the block with respect to stationary observer on the ground is equal to magnitude of normal reaction. From Newton's second law, that can be equated to m into a. But magnitude of the static friction between the two surfaces in contact less than or equal to the limiting value in US into n. So you can substitute here n equal to ma on the right side and Fs equal to mg on the left side. So when the block is stationary with respect to the cart, you can write mg is less than or equal to nu s into ma, or g is less than or equal to nu s into a, or you can write nu s into a is greater than or equal to G. So block will be stationary with respect to the cart. If the acceleration of the cart is greater than or at least equal to G by US, therefore the minimum acceleration with the cart has to move horizontally so that the block remains at rest related to the cart is G by US. Come on, copy down the solution of the problem. In case you need more time to copy the solution of the problem, you can take a pause and take your own time. So for question number 52, first option is answer. Next I am going to discuss question number 53. So block rests on a rough inclined plane making an angle of 30 degrees with the horizontal. The coefficient of static friction between the block and the plane is 0.5. If the frictional force acting on the block is 10 newtons, the mass of the block is. So you can hear the coefficient of static friction between the block and the inclined plane is 0.8. So tan theta is tan 30 degrees, which is equal to 1 by root 3. The value of 1 by root 3 is definitely less than 0.8. That means in this case tan theta is less than US. Or you can say the angle of inclination of the inclined plane to the horizontal is less than tan inverse US, or angle of inclination of the inclined plane to the horizontal less than the angle of friction or less than the angle of repose. Therefore, the block will be at rest on the inclined plane. As explained similar question in the past. So when the block remains at rest on the inclined plane under action of its weight mg, normal reaction and static friction, then magnitude of static friction on the block by the inclined surface same as the magnitude of the component mg sin theta. Actually similar problem I have discussed in the past. That's why I am not showing the free body diagram. For this problem, same model I have discussed in the past in the same assignment. But I am repeating this model because this problem is originally given in one of the previous IIT-JEE entrance exam papers. So magnitude of friction, static friction on the box by the inclined plane is given to be 10 newtons. G is given to be 10 meter per second square. Sin theta to sin 30 degrees is 1 by 2. So from this you get mass of the block to be equal to 2 kg. So for question number 53, fourth option is answer. So here, look at the question number 54. The upper half of an inclined plane with angle of inclination phi is perfectly smooth, while the lower half is rough. Body starting from rest at the top will again come to rest at the bottom. The coefficient of friction for the lower half is given by. So here, the block moves from A to B for the upper half of the inclined plane. That means the part of the inclined plane from A to B is smooth and part of the inclined plane from B to C is rough. So A is the initial position of the block at the top of the inclined plane. B is the final position at the middle of the inclined plane. At the end of, final position for motion down the rough and smooth inclined plane. Let V1 denote the magnitude of the velocity at the middle of the inclined plane. So for motion from A to B down the smooth path of the inclined plane, the magnitude of acceleration is given by the formula g sine theta. Here theta equal to phi. Phi is the angle of inclination of the inclined plane to the horizontal. Don't mistake phi as the angle of friction in this problem. Phi is not the angle of friction here. Phi is used to denote the angle of inclination of the inclined plane to the horizontal. So if you use the formula Vf square minus Vi square is equal to As. Here S is the magnitude of displacement for motion down the smooth inclined plane. The magnitude of displacement for motion down the rough inclined plane is also equal to S. That means the length of the smooth part of the inclined plane is same as the length of the rough part of the inclined plane. That means total length of the inclined plane is S plus S or 2S here. The final velocity at the end of the smooth part of the inclined plane is denoted by V1. Initial velocity at the top of the inclined plane is 0. The acceleration when it is sliding down the smooth inclined plane is given by g sine phi. So you get V1 square equal to 2gs into sine phi. Next we consider the motion of the block from B to C down the rough part of the inclined plane. The initial velocity at the beginning of the motion down the rough inclined plane is equal to V1. The final velocity is when it reaches the bottom of the inclined plane is given as 0. Magnitude of the displacement is again the same. So magnitude of the acceleration when it slides down the rough inclined plane is given by g into sine theta minus nu k into cos theta. Here the angle of inclination of the inclined plane to the horizontal denoted by phi. Nu is the question of sliding friction between the block and the inclined plane. This is the formula for a magnitude of acceleration when it slides down the rough inclined plane. It is given that the body starts from rest at top of the inclined plane and comes rest to the bottom of the inclined plane. So motion of the magnitude of displacement for motion down the rough part of the inclined plane is same as the magnitude of the displacement for motion down the smooth part of the inclined plane. So again use the same equation Vf square minus Vi square equal to As. Here Vf is 0, Vi equal to V1. So acceleration is equal to g into sine phi minus nu into cos phi. Magnitude of the displacement is again denoted by S. So you get V1 square equal to minus 2gs into sine phi minus nu cos phi. You can equate the value of V1 square from the two equations 1 and 2. So equate the value of V1 square from first and second equations. So the value of V1 square from the second equation you can write two gs into nu cos phi minus sine phi. If you carry that minus sign inside. And from first equation V1 square you can write 2gs into sine phi. So sine 2gs you can cancel both sides. Come on, simplify this yourself and complete the simplification part yourself. If you want to need more time to copy the solution, you can take a pause and take your own time. So you get, if you simplify this, you get nu cos phi minus sine phi cos phi minus sin phi equal to sin phi. So you get nu cos phi equal to sin phi plus sin phi. So from that you get the value of nu, you can simplify it to yourself. You get nu equal to 2 tan phi. For 54, first option is answer. See the question number 55. Force of magnitude F equal to 24 Newton is applied parallel to the inclined surface. Nu is equal to 1 by 4. Nu k equal to 1 by 5 and a block of weight 100 Newton placed on the fixed inclined plane of angle of inclination. Theta equals sin inverse 3 by 5 to the horizontal t equal to 0. After 1 second, you have to find the magnet of friction force of the block after 1 second. And you have to also find magnet of the axle of the block after 1 second. That means you have to assume that the block is initially at rest and the force is applied on the block at the initial moment. So you must recollect the discussion I have done in the special case 2 and special case 3 for motion on the rough inclined plane. So the block, if a block is placed on the rough inclined surface of a fixed inclined plane, so here tan theta is more than the coefficient of static friction. You can check up tan theta, you will get 3 by 4, coefficient of static friction 1 by 4. So tan theta is more than coefficient of static friction. So if tan theta is more than the coefficient of static friction, so block will be at rest on the inclined plane. Mg into sin theta minus nu s into cos theta less than or equal to F is less than or equal to mg into sin theta plus nu s cos theta. So you can substitute the given values. Come on, copy down. The weight mg of the block is given to 100 Newton, sin theta is 3 by 5. The coefficient of static friction 1 by 4, cos theta is 4 by 5. As I discussed, the block begins to move up along the inclined surface if F is more than mg to sin theta plus nu s cos theta. The block will slide down the inclined plane if F is less than this value mg to sin theta minus nu s cos theta. So here you can simplify this. So the block will be at rest on the inclined plane. And we are analyzing the situation completely. For any magnet of force applied on the block parallel to the inclined surface in between 40 Newton and 80 Newton, it will be at rest. That means the block begins to move up along the inclined plane with an acceleration if kept left is more than 80 Newtons. So for the minimum magnitude of the force to be applied on the block parallel to the inclined surface to prevent the block from sliding down the inclined plane is 40 Newton. That means the block will remain at rest for any magnitude of the force applied on the block, 40 Newton or more than 40 Newton, but less than or equal to 80 Newton. The force applied on the block is less than 40 Newton, then it begins to slide down the inclined plane. So in the given problem, F is given to be 24 Newton, which is less than 40 Newton. Therefore, you can conclude that block slides down the inclined plane. You can conclude that block will slide down the inclined plane. Therefore, force of kinetic friction of the block with inclined surface acts up along the inclined plane. So I have shown the free body diagram for the block. The weight mg of the block acts vertically downwards, which you can resolve into two rectangular components parallel to the inclined surface and perpendicular to the inclined surface. The component mg cos theta acts perpendicular to the inclined surface. The component mg sin theta acts down the inclined plane parallel to the inclined surface. I choose the direction of the motion of the block parallel to the inclined surface as positive direction of x-axis. Direction perpendicular to the inclined surface as y-axis. The block is sliding down the inclined plane. Force of kinetic friction on the block acts up along the inclined plane. So y component of resultant force of block, you can write n of mg cos theta, which will be equal to 0. So magnitude of normal reaction, the block is same as the magnitude of component mg cos theta. So magnitude of kinetic friction of the block is equal to nu k to m, that is equal to nu k into mg cos theta. So here nu k is given to 1 by 5. The weight mg of the block is 100 newtons. Cos theta is 4 by 5. So I get magnitude of kinetic friction on the block as 16 newtons. That is one of the answers. Then y component resultant force is 0. The resultant force of the block is equal to x component resultant force. So the component mg sin theta acts down the inclined plane parallel to the inclined surface in the direction of the motion of the block. Fk represents magnitude of kinetic friction. It acts opposite to the direction of the motion of the block. Capital F is the magnitude of the force applied on the block parallel to the inclined surface, which also acts opposite to the direction of the motion of the block. So x component of resultant force of the block has magnitude mg sin theta minus Fk minus F. Weight mg is given to 100 newtons. Sin theta equal to 3 by 5. Magnitude of kinetic friction is equal to 16 newtons. F is given to 24 newtons. So you can simplify this. So you get magnitude of the x component resultant force as 20 newtons. So we take G as 10 meter per second square for this problem. So weight mg of the block is 100 newtons, G is 10 meter per second square. You get the mass of the block as 10 kg. From Newton's second law, magnitude of the resultant force of the block is equal to the product of its mass and acceleration. So magnitude of the resultant force is 20 newtons, mass of the block is 10 kg. So you get magnitude of the acceleration of the block is 2 meter per second square. That is another answer. So the block has an acceleration of magnitude 2 meter per second square down the inclined plane. In case you want to copy the solution, you can copy down the solution of the problem. In case you need more time to copy the solution, you can take a pause. So for question number 55, magnitude of friction force on the block is 16 newtons up the inclined plane. That is, statement B is true. The magnitude of acceleration of the block is 2 meter per second square down the inclined plane. So in the question number 55, the statement date should not be up here. It should correct it as down, that means here you have to correct this statement D. That means instead of up, it should be written as down because the previous option is written as up. So acceleration of the block is 2 meters per second square down the plane. That means statement B is correct, statement D is correct. That means the second option is the answer. So this problem, see here, question number 56. Block of weight 130 Newton is at rest on the inclined surface of a fixed inclined plane, and the magnitude of friction force the block is 50 Newton. Force is applied parallel to the inclined surface, which is just sufficient to start the block moving down the inclined plane. And if the same force is maintained even after the motion begins, then acceleration of the block in meter per second square will be, take GR 10 meter per second square. This problem comes under one of the special cases I discussed earlier. You see the last special case which I have discussed for motion on the rough inclined plane. You can see the last special case which I have discussed for motion on the rough inclined plane. So here the block is at rest on the inclined plane because similar discussion I have done in 2 questions in the past. The block is at rest on the inclined plane. If the block is at rest on the rough inclined surface of fixed inclined plane under the action of its weight mg and forces by the inclined plane, then magnitude of static friction on the block by the inclined surface same as the magnitude of the component mg sin theta which tends to move the block down the inclined plane. Magnitude of static friction on the block by the inclined surface is given to 50 newtons. The weight mg of the block is given to be 130 newtons. Therefore, you get sin theta equal to 5 by 13. From this, you can find the value of cos theta. You must be knowing how to calculate the value of cos theta when you know the value of sin theta. It comes out to be 12 by 13. So tan theta is 5 by 12, which is less than the coefficient of static friction. That means here tan theta is less than US, or the angle of inclination of the inclined plane with the horizontal less than the angle of friction between the two surfaces in contact. That's why the block was initially at rest on the inclined plane. So in one of the special cases I have discussed here, the force is applied on the block parallel to the inclined surface, which is and down the inclined plane, which is just sufficient to start the block down the inclined plane. And if the same force is maintained even after the motion begins, then magnitude of the acceleration of the block is given by nu f minus nu k into g cos theta. So if the problem is given an objective type of paper, you can directly use this conclusion. So you can substitute the values given there. Nu f is equal to 3 by 4 means 0.75. Nu k is 0.62 and g is 10 meter per second square. Cos theta is 12 by 13. So you can simplify this. So you get magnitude of acceleration as 1.2 meter per second square. If you want to copy down the solution of the problem, you can copy down the solution. So for question number 56, first option is the answer. See the question number 57. A student is cleaning a blackboard by moving a light duster up and down on it. The coefficient of static friction between the duster and the board is US. The duster will not move up no matter how large the force is. If you have to find out which option is correct. See the question number 57. So I have drawn the free body diagram for the block. You have to find, let us first find the condition for which the duster can move up on the surface of the blackboard. So when the duster begins to move up or about to move up along the surface of the blackboard, the force of friction on the duster by the surface of the board acts downwards, opposing the motion of the duster in the upward direction. So when the duster tends to move up or about to move up on the surface of the blackboard, then force of friction on the duster by surface of the board acts vertically downwards. F is the force applied on the duster by the external agent or by the student. N is the measure of normal reaction force on the duster by surface of the board, which acts perpendicular to surface of the board and directed away from surface of the board. That means in this case, normal reaction force acts in the horizontal direction, perpendicular to surface of the board and direct away from surface of the board. So I choose the horizontal direction as x-axis and vertically upward direction as y-axis. Can resolve this force F applied by the student into rectangular components along horizontal and vertical components. The component F cos beta acts vertically upwards. The component F sin beta acts in the horizontal direction. So X component of the force is equal to F sin beta minus N. That can be taken as 0. Or F sin beta equal to N. So duster can to move up on the surface of the board. F cos beta, which tends to move the duster upward, should be more than or at least equal to mg plus magnitude of limiting friction, which is equal to nu s into n. You can substitute the value of n from this equation here on the right side. So F cos beta has to be greater than mg plus nu s into F sin beta. You can collect the terms containing F to the left hand side. So therefore, to move up, the force applied has to be more than mg into cos beta minus nu s into sin beta. That means minimum value of the force to be applied by the student to move it up has magnitude equal to mg into cos beta divided by cos beta minus nu s sin beta. So it is possible to move up by applying any magnitude of the force more than the above value if the denominator on the right side is positive, because F minimum represents the positive value, the magnitude of the force to be applied by the student. So nu F sin beta has to be less than cos beta, or sin beta by cos beta should be less than 1 by us. So tan beta has to be less than 1 by us. Only then it is possible to move the duster upwards by applying any magnitude of force more than this minimum value. That means if nu F sin beta is suppose more than cos beta, then denominator will be negative. That means it's not possible to move up if nu F sin beta is more than cos beta, or it's not possible to move up by applying any magnitude of the force if tan beta is greater than 1 by us. So I will continue my discussion in my next class.